So what we're going to be looking at now is something called the ideal gas law. Okay, basically the ideal gas law is really just this equation here. Okay, and it gives us a way of kind of dealing with gases and letting us calculate, pressures and volumes and sort of different I guess, properties of a specific sample of gas. So this equation here is what we call the ideal gas law. Okay, so we've got pressure given by P, volume given by a capital V, mole given by N, temperature given by capital T, and then this constant R. Okay, now R here is basically something we call the ideal gas constant. Okay, and it has a value of 8.31 joules per Kelvin per mole. Okay, now it's really just the number that's important here. Okay, just the number is important here. This unit of joules per Kelvin per mole, it's kind of a bit, we can't really take much from it. We don't really understand what this means physically or what it means in terms of a gas sample. However, it kind of just has this unit in order to ensure that this equation kind of, all the units cancel out nicely, okay? So really it's just the number 8.31 that we're looking for, okay? And as this name suggests, this law, this equation is appropriate for ideal gases, okay? Now ideal gases are kind of theoretically, perfect and nice and easy to deal with gases. However, this equation still provides, a very good calculation for non-ideal gases, which is what we're usually going to be dealing with. However, even in those cases, we can still use this ideal gas law. Okay. Now, a few things that we need to know about the ideal gas law are, firstly, the standard units. Okay. Just like any equation, we have to make sure we're using the correct units for all the calculations and measurements that we're plugging in to ensure that we get the right result. Okay. So we've got here the standard units for pressure are pascals, given by PA. Standard unit for volume is cubic meters. The standard unit for mole is basically, obviously, mole. And the standard unit for temperature is Kelvin. Okay, now a few things we need to know, a few unit conversions that we're going to have to make. I'm going to fill you in on those here. Okay, so basically, pressure is given by pascals when we're using this equation. However, often we'll be given a temperature in the unit called an atmosphere. Okay, and this atmosphere is given by the abbreviation ATM. Basically, one atmosphere is basically the temperature of our Earth's atmosphere at sea level, okay? That's not really important, but what is important is that one atmosphere is equal to 101.3 kilopascals. Okay, so if we're ever given a temperature in atmosphere, say we're told a gas is at a temperature of 5 atmosphere, okay, then we can just convert that by multiplying this number by 5, and then we have 5 atmosphere is equal to a certain number of kilopascals. Okay, similarly, we may often be given volume in liters rather than cubic meters. Okay, so if we go 1,000 liters is equal to 1 cubic meter. Okay, so that's another one that we're often going to have to make. Often we'll be told, a gas sample has this many liters big, so we'll convert it to meters cubed before we use this. Okay. Lastly, temperature. Kelvins aren't a unit that we often deal with in our day-to-day life. We're used to using degrees Celsius. Okay, but basically, what we need to know is that 0 degrees Celsius is equal to 273 Kelvin. Okay, so 1 Kelvin is basically equal to 1 degree Celsius. As in a step of 1 Kelvin is equal to a step of 1 degree Celsius. However, degrees Celsius can go down to a value of negative 273, okay? And we can't have negative temperatures floating around in an equation like this, okay? So basically, what we've done when we're using kelvins as our unit for temperature is we've basically just added 200, we're just adding 273 to whatever the value of degrees Celsius is. And that's the number that we're using, okay? Just to ensure that we don't get any negatives, okay? And so the lowest possible temperature we can have in kelvins is 0. And that way this equation can still work, okay? One more little piece of information that's pretty handy to know. Okay, here we've said that pascals are supposed to, the units of pressure are supposed to be pascals, and the units of volume are supposed to be meters cubed, okay? Now, having said this, it is allowable for us, as long as we change both pressure and volume, we can use pascals, we can use pressure in kilopascals, and we can use volume in liters, okay? Now, this is only allowed if we do both, okay? Either we have to use pressure in kilopascals and volume in liters, or we use pressure in pascals and volume in meters cubed, okay? We can't kind of swap and change between these two sets, okay? Either pascals and meters cubed, or if we want, kilopascals and liters, okay? And basically this is allowed because a liter is 1,000th of a cubic meter, and a kilopascal is 1,000 times a pascal, okay? So these factor of positive 1,000 and negative 1,000 kind of cancel out here when we have P times V, okay? So that allows us to use kilopascals and liters at the same time, or we use pascals and meters cubed, okay? We can't swap and use liters and pascals, for example. That will give us the wrong answer. Okay, the last little bit that we're going to deal with regards to the ideal gas law is something called molar volume, okay? Now, molar volume is pretty straightforward once you get your head around it. Okay, basically, what we have is we have two sets of standard conditions, okay? One is called standard laboratory conditions, okay, and we abbreviate that by SLC. The other is standard temperature and pressure. Okay, these two abbreviations, the standard laboratory conditions and standard temperature and pressure, basically refer to a standardized set of conditions that we may use when we're dealing with a gas sample. Okay, so standard laboratory conditions refers to a temperature of 273 kelvins and a pressure of, sorry, not 273, let me correct that, to 298 kelvins and 101.3 kilopascals. So that's pressure. Okay, now standard temperature and pressure refers to a temperature of 273 kelvins. Okay, and again, the same pressure of 101.3 kilopascals. Now we can figure out these two things from the ideal gas equation. However, these standard sets of conditions give us a shortcut. Okay, what they give us is a volume, a molar volume. Okay, we'll abbreviate this by VM. Okay, and I'll explain to you what this means in a second. So, if we say that we have a molar volume of 24.5 liters per mole. Okay, what that means is that if we have a gas sample at this temperature and at this pressure, then no matter what gas we're talking about, okay, every mole of that gas is going to occupy a volume of 24.5 liters, okay? So this is kind of a standard condition, a standard volume per mole, okay, that we can use when we're dealing with standard laboratory conditions, which I've given here. Okay, similarly, if we're talking about standard temperature and pressure, then the molar volume is equal to 22.4 liters per mole. Okay, so again, if we have, 5 liters of something at standard temperature and pressure, then rather than plugging into all the numbers into this equation, we can use this molar volume to sort of quickly find the answer and the number of moles that we're looking for. Okay, but only if the conditions fit one of these two standard sets. Otherwise, we do need to use this full equation. Okay, so I'll go through a couple of examples of molar volume and of how to use the ideal gas law in another video.